Here we are talking about 4.5, linearization and differentials. Two topics that you will never ever use outside of my class. Just kidding. You're going to use this stuff all the time. Actually, you're not. Well, maybe some of you will. All right. Anyway, here we go. In front of you is the equation y equals root x in its graphical representation. I want to try to estimate the square root of 4.01. Now, I'm not going to do this with a calculator. I want to use calculus. Yes, I could just type that into the calculator, square root of 4.01, and get an answer. I don't want to do that. I want to use a technique called local linearization. That curve, y equals root x, is actually made up of a bunch of straight lines. If I were able to zoom in at the point 4,2, where the pink dot is, I would see that that's actually a straight line. Well, I can use that straight line to try to estimate the square root of 4.01. So let me show you how I'm going to do that. I'm going to go ahead and find the tangent line at x equals 4. If it's a tangent line, I'm going to have to find the slope. The slope is going to come from the derivative, dy dx. The reason why I'm doing this, I said it's local linearization. If it's a linearization, a line would be the tangent line. So dy dx is going to be as follows. Rewrite the square root of x as x to the 1/2, then just use your power rule. Dy dx is as given here. Now I want to evaluate that at x equals 4. Instead of x to the negative 1/2, I'm going to write that as the square root of x in the denominator and plug in a 4 for x. That's going to give me 1/4. This is my slope of the tangent line at x equals 4. And then to find the tangent line, I'm using the equation in pink. Y minus y1 equals mx minus x1. I already have my x1 and y1 values. I'm trying to find the tangent line at x equals 4. So x1 equals 4. y1 is going to be the square root of 4, or 2. Go ahead and plug in your slope for m while you're at it. You get y minus 2 equals 1/4 x minus 4. And I'm going to clean this up, getting y equals 1/4 x minus 4 plus 2. All I did was add 2 to both sides. And now I'm going to use this equation to estimate the square root of 4.01. I'm going to go ahead and plug in 4.01 for x. 1/4 is 0.25, and then I'm just going to simplify this equation. 4.01 minus 4 is 0.01. Then multiply that by 0.25 and add 2. And you'll get an answer of 2.0025. This estimates the square root of 4.01 without a calculator. I'm using local linearization. I'm saying that this function is growing at a rate of 1/4. And if I know the rate of change, how fast is the function growing at 4, I should be able to use that to estimate the square root of 4.01, which is a point just to the right of 4. So what I've done, instead of evaluating the square root of 4.01 on the curve, I evaluated it using a tangent line, because evaluating with a line is much easier than evaluating with the square root function. All I did was plug in the rate of change for m and look at the change in x from 4.01 to 4, and then added 2 from the y1 value. Worked all that out, and I have a good estimate. Now, error, how far am I actually off here? Error is defined as the absolute value of the actual answer minus the estimate. So if I took a calculator, the actual square root of 4.01 is 2.002498. If I subtract my estimate, 2.0025, I'll get an answer of 0.000002. That's pretty darn close. That means I'm really, really close to the actual answer. My question now, is this an overestimate or an underestimate? This is going to be an overestimate. And the reason why is if I look at my tangent line in red, my tangent line is above the curve in yellow. The function for y equals root x is concave down at 4. So it's curving below the tangent line. So that means my estimation is a little bit too high. And that makes sense on why my error was a positive number inside the formula absolute value actual minus estimate. So whenever that happens where your tangent line is above the curve, it's going to be an overestimate. If my curve was above the tangent line, that would be an underestimate. All right, so let's go ahead and move on to differentials. If I had a cube whose side lengths were 4 by 4 by 4, I could figure out the volume, 4 times 4 times 4, which is 64. And I guess these would be units cubed. If I wanted to change that side length from 4 to 4.02, what kind of change does that have on my volume? Obviously, it's going to make a bigger volume, but what's the change in that volume going to be? Well, volume in this case is x cubed, where if my cube were made of sides x by x by x, I can take the derivative and get dv dx, the change in volume with respect to x. So I would get dv over dx equals 3x squared. I can cross multiply and solve for dv. Put 3x squared over 1, and 1 times dv is dv, and then 3x squared times dx is 3x squared dx. So my change in volume would be 3, the x value for the side length was 4 squared, times dx. dx is the change in x. When I went from 4 to 4.02, I had a change of 0.02. So this is dx. So calculating that without a calculator, 4 squared is 16 times 3, and then multiply it by 0.02. That's going to give me my change in volume, in this case 0.96 units cubed. Now my question is, so what's my new volume? The volume came from the formula x cubed, which I already knew was 64. 4 times 4 times 4, because x, my original length, was 4. And then I'm going to add to that the change in volume. The change in volume is 0.96. Add these two up, and I have a new volume of 64.96 units cubed. So this one's a little bit more straightforward than local linearization. I'm just using differentials. The only thing I'm doing different here than anything I've done before is I'm solving this equation for dv rather than dv over dx. And again, I did that through cross multiplication. And then I'm just going to plug in all the different variables. The x was my original side length, 0.02 was my change in side length, and then it's just straight calculations from there to get your new volume. So that pretty much sums it up for differentials and local linearization.